Good afternoon. In this video, I shortly introduce you to the work we did in residual quantization with implicit neural codebooks. First, in short, the goal was to improve vector quantization that is used often in compressed similarity search. There you have an incoming query and you want to find a database element that is all of them are compressed that best matches your query. The strategy we took was to improve upon conventional residual quantization by adapting the codebooks to residual distributions. The result, we found a much lower compression error compared to the baselines and a much higher search recall. So let's first all get on the same page. In vector quantization, we have a codebook with k learned quantization vectors or centroids, and a vector quantizer, given an incoming vector, selects the centroid that best matches your vector based on a certain distance measure. Opposed to normal vector quantization, there is multi-codebook quantization, where a vector is represented as a sum of vectors from multiple codebooks. If we have m codebooks, each with k options, then we suddenly have k to the power of m different quantization options, which heavily improves the capacity of a multi-codebook quantization scheme. So let's review residual quantization. An incoming vector x is quantized using the first codebook, and the resulting quantization vector is subtracted from the original vector to get the first residual. And here in this figure, it's called R2. Then we aim to quantize that residual using the second codebook. And the vector that gets extracted from that codebook then again gets subtracted from R2 to get the next residual R3, etc. Let's show it in an illustrative toy example. Here we made a bimodal data distribution and we trained a conventional residual quantizer. The centroids of the first codebook end up at the start positions here, and that leaves us with these residuals to be quantized in the next step. The centroids for the next codebook then ended up here. So we have two centroids in that codebook, but we plotted them around the centroids of the previous quantization step, and you see that that's suboptimal, especially in the left bottom corner of the figure. The centroids of the second codebook do not well cover the residual distribution that clearly depended on the centroid selected in the first step. So our goal was to use codebooks that actually do depend on the centroids that you selected in the previous quantization steps, such that these codebooks get adaptive towards the residual distribution. And quickly already showing the result on this toy data for our model, what happens now is that given the previous quantization selected quantization centroids, the star here, you see that the centroids of the next step, the triangles, are now adapted to the residual distributions that need to be quantized. So how does it work? We started from residual quantization and we wanted to make adaptive codebooks, right? So what we did is we introduced a neural network f theta at every step that updates a given base codebook, conditioned also upon the reconstructed vector so far. So that is the sum of the selected quantization vectors from the codebook so far. And then predicts an adaptive codebook from which we then select the most optimal quantization vector for that step. So our method is called quantization with implicit neural codebooks, dubbed QINCo. For extensive results and ablation studies, you can see the paper, of course, but here I quickly want to show some main results. So here we see that on multiple data sets, the columns, QINCo outperforms conventional methods with standard implementations like OPQ, RQ, and LSQ, but also machine learning baselines like QINCo. It outperforms both in terms of compression, mean squared error, but also in similarity search recall at one performance, for which higher is better. In the right figure, we see that if we look at timings in terms of queries per second on the y-axis, that QINCo extends the Pareto optimal curves for high recall operating points. In the paper, we also show that thanks to the way we train QINCo, QINCo can also be used as a multi-rate codec where you train the model for a certain bit rate, but you can deploy it later for lower bit rates as well. I hope that introduced you to the topic of this paper. If you're visiting ICML, you can have a chat with us, and the poster session 6 on Thursday afternoon.